let me introduce him first. So Dennis Dalessandro is a kernel engineer for Cornelis Networks, leading in the development of OmniPath architecture, hardware drivers. He received BS in computer science from OSU. Over the past 18 years, he has been a researcher at the OSC itself, a performance engineer at NetApp, a driver developer at Intel. Dennis is very active supporter of open source software and enjoys working closely with the kernel.org community and with various Linux distributions. So let's welcome Dennis. And Dennis told me that since he used to work at OSC, he had his desk at that corner. So as soon as he came today,
That's right.
he picked that up. So he's a licensed desk here in this room.
Right.
So.
Mm-hmm.
Yeah. Not coming. Are the slides being shared?
Slides are not coming up that.
Someone is not working here. One second. Sorry for the interruption. Just we'll be taking care of things.
There we go.
Hello, 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 hello.
Hello. Hello.
Okay. Okay, so show the presenter
Yeah.
view and then. Yeah. Okay. Sorry, we are back. Sorry for the delay, Dennis.
That's
Please.
okay.
Please proceed.
Oh, this will work now?
Yeah.
All right. Ah, look at that. All right. You guys can hear me, or at least I hope the WebEx can hear me. All right. So, quick overview. I'll introduce myself here, and then I'm going to talk about what and who Cornelis Networks is. Not everybody might not be familiar with the name. And the main part is, what OPX is and what's so great about it. The Doug, who is our director of software engineering, he is going to give a talk later on in the week, and he'll give a lot more detail on what Cornelis Networks is and where we're going, where we came from. So normally I don't do the whole introduction thing, but this is kind of a cool situation for me here. So I graduated from Ohio State a really long time ago, back in the early days, 2004, and I was a researcher here at the Supercomputer Center. Actually, I was part of the group that started the OSC Springfield. So halfway between here and Dayton, there's we started a site. Eventually came back to here, but I spent many days working from this very theater. That's why I grabbed my seat back there in the corner, and that was back when there used to be monitors and keyboards in front of all the things, because not everybody carried laptops around. So it's good to be back, and I haven't been here for quite a few years, and everything has changed so much. There's a building where there was no building before, and it's good to see how much campus and everything has grown. So it's good to be back. So nowadays I'm a kernel developer, mostly for Cornelis Networks. I kind of serve as our point of contact for the Linux distros. I work closely with the kernel network community to maintain a number of our drivers. And I work really close with the OPX developers, which is, that's what this talk is about. So I may not be able to answer every, detailed technical question about OPX, but I can certainly find out. So if I can't answer something, find me afterwards, and we'll get you whatever answers you need. All right. So quickly, what Cornelis Networks is. There was went through a few startups, and then eventually became bought by QLogic and had an InfiniBand product. It was a QDR product, and I don't know the year, but then eventually Intel came along, and about 2013 is when I joined them, so probably 2012 or so. Doug might know for sure. Intel bought the QLogic group, which was the QIB group, and eventually that became Cornelis Networks after Intel started going a different way. So we spun out of Intel about 2 years ago, which we brought the customers and the technology, the IP. Intel was very instrumental in getting us set up and running, and nowadays we're completely separate on our own, which is has its advantages for us, and I'll touch on that here later. So what we have right now is the OmniPath architecture fabric. It is a 100 gigabit network. Our next generation is a 400 gigabit product. The marketing name is CN5000, so you'll probably start seeing that around. And again, Doug will talk a lot more about that later. So I'm mainly here to talk about OPX, which is our libfabric provider. The eventual goal for this is to replace PSM. So those that don't know, PSM2 is our API that lets you use our hardware. I think it's performance scaled messaging. But so like I said, we're going a different way. We're not dropping PSM2 or anything like that. It's still fully supported, especially on the Gen 1 stuff, but it's not the path forward for the CN5000. So what we have is this thing called OPX. OmniPath Express is the name for it. And basically it's not, we didn't take PSM and just rewrite it or refactor it. It's based on the BGQ provider for libfabrics, which is, I guess, was used on BlueJeans. So it's highly optimized and, you know, it's proven performance. So we do have work to do still. We have upcoming support for various GPUs and the MUG'22. I think the provider is now available, or it will be soon. And we, so the important thing is it doesn't require any changes to our hardware or our fabric manager, our driver. It really is just a drop-in replacement. It's just, you know, user space software. So this is, you know, a picture of what the software stack looks like. We got all these red boxes here on top. Those are really what this is showing is the benefit of libfabric. So we get all of these different applications and things that, you know, that work with our hardware by only having to support, you know, libfabric. Whereas with PSM2, we have to have everything, you know, has to have its own code and everything. So this is, like I said, just kind of showing the overview of that. One interesting thing here is, so you'll see the Intel MPI box and how that's kind of, you know, multiple colors there. That's technically goes over libfabric, but it actually goes back through PSM2 afterwards. So it's a very unoptimal path. And of course, we support all the usual verb stuff. This slide says UDAPL. I don't know if anybody still uses that or has even heard of that.
Just a quick question.
Yeah.
So the HPC community is very focused on that last bit of performance you get, right? So is there any potential benefits in using like PSM2 or PSM3 directly instead of going over OFI? Like you say that Intel MPI is like half red and half blue. Right.
So I'll show that here in a second. So as opposed to libfabrics or our OPX provider in libfabric, the code is so much more efficient that it actually it makes up for that difference in having kind of another layer. But it's really not. So PSM, when you look at PSM is basically like what libfabric is. It has multiple layers in it, and the code is just not as efficient as it could be. And so you talk about that last little bit of performance in HPC, and that's specifically why we do this. And I've got a cool stat here I'll show at the end of, you know, why that OPX is actually better than going through PSM2.
Right. So a few years ago, Sayantan, while he was at Intel, had shown some numbers mentioning how many instructions it takes from like a high-level send to going out the network.
Yeah.
Would you be having something like that?
That's exactly. I got it.
Okay.
For the receive, because that's our hottest path. But yeah, that's exactly the reason is for that, for reducing instructions, the cache lines, and you know, it's that last little bit that really makes a difference in the performance.
Okay, thank you.
And just to note, so PSM3, I mean, you mentioned that. So PSM3 actually has nothing to do with PSM2. PSM3 is an Ethernet thing that was based on PSM2. So I guess that has something to do with it, but it has nothing to do with OmniPath. It's purely Ethernet. And there's something you said about PSM2. I mean, it's been around for, 10, 15, 20 years. I don't know at this point. I mean, it's been around forever. So it's got a lot of it's got a lot of engineering work that's went into it. So it does, it is very good. So the fact that we're able to actually, this quickly get better performance is, it's a testament to, how good these guys are that are working on our OPX thing. So this is kind of showing what the existing, way of doing things is. So that's the blue boxes there. So this is where, the application, works with MPI for evapitch, which talks directly to PSM2, and then, can go through our hardware, our driver. That's the pro here is obviously it's, we have direct access with PSM2, like we were just saying. There's fewer layers, but the downside is that it's yet another API that the MPI library has to implement and support. And for us, like I said, PSM2 is not the path forward for OPA 400 or CN 5000, which is the product name. So we kind of looking to do something different. The other way of kind of doing this is what I was showing with that multicolored box there. So, we have, for instance, Intel MPI is the, the notable one. It goes through the libfabric and then actually calls into PSM2. So it's kind of doing double duty here. It's, it allows, we get the benefit of having the single API and all those applications and everything. But the con is that, it's not an optimal code path. And when you get down to it, PSM2 it's not a semantic match to what libfabric wants to do. Libfabric was, is kind of designed to be, a better version of doing things better, solving the problems that verbs, that verbs had. And PSM2 is, something completely different. So they don't mesh together very well. And that introduces, obviously performance issues. So what we do now with our OPX is the libfabric itself actually supports OPX. So the OPX is part of libfabric. So OFI libfabric, they have, this architecture where they have multiple different providers for the different hardwares, and it's all hidden in there. So we get that benefit of having this single API for applications or for middlewares to code to. But yet it still retains that performance to be able to access our hardware directly. So we get the same benefits as the direct to PSM2. And it's also, based on a provider that has proven performance. Like I said, it's based on the BGQ provider. The downside is that it's a new provider. It's new code. It takes time to upstream things, and upstream first is a very important principle for us at Cornelis. So that's there's challenges that come with that, but it is available now, and I'll talk more about that. So I guess I wanted to mention the different ways that software and stuff can access our hardware. This seems to be a point of confusion for people because it's very different than other competing technologies. So looking more in the technical details, there are calls into the kernel with various driver ioctls, and this is to do stuff that is not necessarily in the critical path. This is to create user contexts, which are turn out to be the endpoints in OFI speak. It like I said, discover details about the hardware contexts. So context is a very overused term. We have resources on the chip. That's what that's referring to. It's used for registering TID receive buffers. So TID receive, that is our tagged receive. That's how we can land things directly into user memory. And then there's a bunch of other stuff that's not directly involved in data movement. There is also memory maps that we use. That's how PIO buffers get accessed, and I'll kind of explain what PIO buffers are here in a sec. Yeah.
So you mentioned about tag receive. So is this like offloading the hardware tag matching?
Kind of, but it's specifically to land it in user buffer. So it's not
Okay.
like a generic tag matching kind of thing.
Okay, thanks.
So yeah, okay. So memory maps. So the user applications memory map a chunk of memory, and that's what gives direct access to the PIO buffers. Let's see here. We also have an eager array in the header queue. Those are all accessed with the memory map. So it doesn't necessarily go through the driver, but it's got to go through the kernel and all that stuff. We have a write V interface, and this is so we can send in a list of SDMA requests, SDMA is a way of pulling data into the card. Right. So the important thing to note here is that we're not actually copying the data or writing the data through that interface. It's just descriptors about the data, and the card is actually responsible to go get that. So the things that we can access directly on hardware, the PIO buffers, like I said, and then there are things that go through the kernel. So the SDMA engines, which goes to the write V. So the driver does do some work. So the type of buffers that I was kind of mentioning here. So we got PIO and SDMA. So PIO is the programmed IO, the memory map stuff. So basically, it's the CPU is involved to actually move the data from the user buffer into the card. With SDMA, it's different, and that's where we have 16 DMA engines on our card, and those go and actually pull the data from the user buffer. The PIO support, that is in the version that's upstream now in libfabric. SDMA is coming very soon. I think it's code complete. It's going through the final stages, and then it should be posted very soon here. On the other side, the receiving side, we've got eager and expected buffers. So the eager are chip resources that are set aside as packets come in, they land in there, and then they're handed out to the user. That's available now. The expected receive, which is the TID, the tag stuff, this is coming. It's still in progress right now. So this is kind of older performance data. Some people may have seen this before. I'm waiting to get newer data here that's publishable, so that should be coming soon. But for now, I at least wanted to show the gains that we are getting over PSM2, and that's what this is showing. So this is OPX versus PSM2. See, we've got about 20% better latency. Our message rate goes up, and we're looking better on scalability. And this is for an Intel platform. And one of the benefits of that we're not Intel is we can work closely with AMD. So we're talking to them, working with them, and these are performance numbers on AMD platforms. And we see the same, similar benefits. Can't compare these to it's not to compare these to the ones before. They're two totally different platforms and everything, but we do see the same trends here, that OPX really does outperform PSM2, and that's why it's our way forward. So why is it better? So other than the fact that we get all those applications supported, it's basically it's a semantic match for libfabric. So which makes sense because it's a provider for libfabric. It's optimized for performance. So when you look at the code, it may not be as what textbook software engineering wants to do. It's performance is what matters 100%. So there may be code repeated or something, or different things like that. The goal is, like I said, performance, not to make it easy on developers. Developers are going to write to libfabric. They're not going to write to this thing. So the instruction count, the cache line, footprint, all that stuff really comes into play and really matters. It focuses on libfabric, like I said, and PSM2 being kind of a general thing, PSM2 does basically what libfabric does, but libfabric is obviously universally accepted. And then here's an example that I pulled from one of the slides that somebody else had done before. This is showing these numbers from this Intel SDE tool, and this gives you all kinds of cool information. The important things that I pulled out of it are, the instruction count, the path through the OPX provider is much more efficient. It takes a lot less, code to accomplish the same thing. And this is, like I said, this is for a receive, and receive is the hottest path that we have. It's the one that directly impacts latency the most. The number of cache lines that we use is reduced, and especially the number of cache lines that, new cache lines that we have to dirty. So, I mean, you can see those are pretty significant improvements, 59% for, new cache lines, and 60%, I mean, they're all about 60%. And this is what, gets us that little bit of extra benefit on the latency. As far as, where things are currently, I'm told the MVAPICH 2 numbers are actually looking pretty promising. I don't have any of those to share. I don't know, maybe Dr. Pena will, his team might have some to share. The OPX code is upstream. It's available as of the 1.15 version of libfabric. It does focus on the small messages and latency first, because that's the hardest part to eke that last little bit of performance. I mean, we can get line rate. I mean, everybody can get line rate. It's that last little bit that matters. The next up for optimizations, the large message improvement, I said that, that's the upstream release is imminent. We are also working on Deos, which is a file system thing, and GPU support, as well as actually declaring it full GA. So I guess we kind of call it beta version or whatever that's in there now. It's available on GitHub. It'll be in the distros, just subject to whenever the distros pick up that version of libfabric. It's also in our OPXS software suite. Those familiar with our product, we had a thing called IFS before, and that's just the new name for it. The best place to get it, though, is to just go to libfabric's GitHub and check out the main branch, and you'll have it there. And, we're happy to take patches and improvements, so feel free. And that's all I got.
Dennis, questions. Dennis? Yes, sir.
We are not letting you go yet. There are a few questions online.
Yeah.
Arpan,
Yeah.
you want to go?
Yes. So there is a question from Dr. Mahesh. Is IP over F is equivalent to IP over IB?
Is IP over F equivalent to IP over V? Yes. That's the term that marketing people like to call it, IP over fabric, since we're not InfiniBand, but it's literally the IP over IB kernel driver that it uses. So yeah,
Okay.
It's the same thing.
Thank you. And there is a follow-up question. What kind of loads and application domains it addresses?
I'm sorry, what?
So what kind of loads and applications and domain it addresses?
I guess anything that you would normally do with HPC, for, the same stuff for that you would normally use MPI for. The libfabric, though, can be used for more than just MPI. There's lots of direct things. The artificial intelligence is that's a big area, as well as wanting to work with GPUs. So those are the kinds of things that we're looking at using and doing.
Okay. Thank you. That's all. No.
Okay. All right.
Thanks a lot again.